we are still organizing the course, and we decided that the final grade of the course will be 80% the final exam and 20% will be the homework. Usually it's a bit less the homework, but due to the circumstances, we want to give you a little bit of bonus, a little bit of advantage. So yeah, I hope you solve the homework and learn by yourself. So what are we going to do today? We're going to study the Laplace equation. And if my handwriting is too small, then tell me, because someone already complained. The Laplace equation. And this is a famous equation. I think you saw some aspects of it before. I'll try to emphasize a few physical insights and also repeat some methods of solving the problems, especially towards the end, some unique problems where usual techniques don't work a little bit, or I hope you don't know about this part of the course. So it will be hopefully a combination of technique and some physical insights. So just as a reminder, we have the usual Gauss differential law for the electric field given by this famous equation. With this famous equation we described last week. This is essentially the Coulomb law in a disguise. It comes from the 1 over r squared law and the superposition principle, where rho is the density of the charges that you have in the system. We also know that the rotor of E is equal to 0. This actually comes from Maxwell's equation. And put together, if the rotor of E is equal to 0, then we can have a potential field V, which depends on the coordinates of space. And that's very nice, because instead of an electric field that has 3 components, it's a vector. We have one potential, which is a field. It's a scalar field. And this rotor E equals 0 means that we can write the electric field like this with the del operator. And from this we can plug it in and we can get a famous equation which is called the Poisson equation. The minus here comes from the definition of the potential. This is called the Poisson equation. And now what we're going to do is we're going to say goodbye to the density, and we are going to solve this equation, which maybe look a little bit silly if you don't know physics, because if we throw away the charges, there's no charges, and if there's no charges, then there is nothing, right, in electrostatics. And I already hinted to this issue. It's not that the charges do not exist. There are some domain in space where there are no charges. Let's say here there are no charges, but maybe far away there are charges. And then this potential can be determined on some boundary. And from this boundary condition, we will determine a non-trivial solution to this potential field. So the general problem is, let's use a notation. We have V, big V, which is the voltage, and we have a volume. I'll call it small v or nu, whatever. And inside here, let's say we have some charges. They are fixed, otherwise we don't have electrostatics. And then we have some point here, and we ask what is the potential over here. This is the general problem, and the boundary can be very complicated. If the boundary is very complicated, we cannot solve it. We can use numerics or whatever. And if the boundary is simple, okay, there are all kinds of techniques to solve them, and this is the name of this game. And then the question is, how do we generally proceed? So to solve this, and this is the most important part for you if you want to pass the exam, what we need to do is we need to work with the Laplacian in all kinds of coordinate systems. This can be Cartesian, cylindrical. I will not use elliptical. The three ones that you should know are Cartesian, spherical, and cylindrical. And they are given also in Griffith's book, so you can review this, and you can know, if you don't remember, you don't need to remember it by heart, but you need to know the Laplacian. You can look it up and use this as an equation. So in general, we have these type of problems. Let's say we have a boundary on a box, because we are all, let's say, this is just a schematics with different potentials on each one of the surfaces. And obviously, in this case, we're going to use Cartesian coordinate to solve it either inside or outside. And always there are two types of solutions. Some of them are inside and some of them are outside. When we say outside, usually also we mean sometimes at infinity, the potential is determined to be zero. So these are important things. And there's always a difference between the inside solution and the outside solution in the body. And of course, this is only for one body. If you have more than one body, it might be more complicated. We might have something like this, which are two spheres. And here V1, and here V2. And obviously, if we have here this obvious symmetry, which is a spherical symmetry, then you'll use spherical coordinates, and you might have something more complicated that we will discuss later, something like that, which is an interesting problem. Here we have a cone, here we have an infinite surface. The surface might be this table or some other surface, a membrane or whatever. And here the potential is zero. There is some angle opening. And here we have V1. Here actually we should always also it's not obvious what coordinate system you'll use in 1 second, but actually here you can also use the spherical. If you have an infinite line, you might want to use the cylindrical, etc., etc. So and then now what happens that in each type of coordinate systems there is a different Laplacian. And in each type of coordinate systems, there are special functions. The special functions in Cartesian coordinates, we will show it will be the exponential decay or exponential growth, or the cosine and the sine. Here it will be Legendre polynomials. There are Bessel functions and cylindrical column. So what I'm trying to remind you is that there's a lot of toolbox and a lot of games to play, and you need to start tidying this in your mind, how to solve different problems and refresh yourself all these type of different functions. And we will discuss a few, and in the exercise there will be few, but all of them are going to be important and possibly in the exam within the more or less the domain of Griffith books, and with a little bit of extensions from Nadav Schneer's group. I'll talk about one extension today, maybe, if I have time. Okay, so we have this equation. What is the Laplacian? I don't know if I should write it, but I will. After the alarms, we should be very silly today. If you woke up in the middle of the night, or I don't even remember when we woke up. This is the Laplacian in Cartesian coordinates, so it's very elegant. Second derivative with respect to x, y, and z. Very simple. Appears also, for example, in the Schrödinger equation, so it's very important, the Laplacian. Okay, so we have this operator, and we have this equation, the Laplace equation. So the first thing to do when you have an equation in physics, you should make it as simple as possible before doing anything. And how do we make it as simple as possible? We say, okay, let us work in dimension 1. We know that the world is not a dimensional 1 world, but let us start with this, because that's... And then we were going to ask questions about the solution of the Laplace equation, and then we'll get inspiration from dimension 1, and then we can say, is it similar in dimension 2, 3? It might be similar and it might not, but this is the way I think about any problem. Let us see what we can do. So in dimension 1, this is a trivial equation, V equals 0. And let us say we have a domain. This is x1 and this is x2. And we are now inside this domain. I'm looking at x inside. It's like I'm looking at the solution inside the box, not outside the box. Okay, and then okay, so this is a simple equation. I think all of you know the answer. What is the answer? What is the answer? Is simply Vx Ax plus b. High school equation. This is the slope, and this is the intersection with the zero. Yeah, the usual thing, the usual linear curve, because you immediately see the second derivative of x is zero. A constant is also there. And we have two constants here, a and b. And why do we have two constants? It's because we have two second derivatives here. And how are these constants determined? Well, actually, there are several ways to determine, but one way would be, let us determine the potential here and here. If we know Vx1 and Vx2 are given, so someone needs to tell you what they are. And what does it mean that on these surfaces, on the boundaries, physically it means that if you bring a charge from infinity, this will be the amount of work you do. So there is a physical meaning to these potentials. Then we can get A and B. I'm not going to even calculate this because this is a linear curve. So we solve the problem. Essentially, we solve the problem. But now let us start thinking about it. How does it look? So this is V as a function of x1 and x2. And for example, this is a linear curve. It goes like that. It could go down. I just plot some curve. It's going up like this. And now we start, okay, now the mind starts thinking a bit. We want to turn this into some physical problem. What is the physical problem? Okay, this will be the theme of one theme of the course today. I want to build a trap. I want to trap you guys in the class. Okay, so I'm trying to be a good teacher. No, I'm serious. Let's say I have an ion or a charged particle, and I want to put it more or less here in space. Why would I like to do that? For precision measurements, quantum computers, I'll talk a little bit about that later. But I want to control. I just want to put it here. And then let's say I also want to do that with electrostatics. So what does it mean, a trap in one dimension? It simply means we put a charged particle inside this potential, this silly, stupid linear potential. There are some dissipation. It loses energy, like we assume it reaches a steady state, the lowest energy by dissipation. Where will it be? It will be here, right? That's going down in energy. You can argue if it's plus or minus, it doesn't matter. My point is, if it's a plus charge or minus charge, the point is it goes to the boundary. The extremon is on the boundary of the system. Now, if you have a little bit of imagination, so let us say that this is also true in higher dimension or more realistic, soon we'll show that it is. What does it mean? You have a boundary. That means, okay, I have a boundary, let's say here, and then I have another boundary here, another boundary here. What are these boundaries? These boundaries are some charge configurations, whatever you make. Some clever company in Japan built some configuration of charges. And let's say the minimum, the maximum of the potential is always on the boundary. Is this good for you or bad for you? It's very bad for you. Good, because you want this ion to be somewhere in free space, like here. Why do I want to put it here? Why is this important for physicists? So it's important for physicists. Let's say we want to measure the energy levels of this ion, or something like that, or the spin of the ion. You don't want it to be next to the boundary, because then you're going to measure the boundary, because how can you distinguish? The boundary itself is composed of all kinds of physical systems. So you want to put it in midair. Of course, later from technology, if you can put it here, then I can put it there, I can put it there, I can control it. This is the engineering point of view, which is also super important. So, okay, in one dimension, we cannot do that. Here is the solution, again, only with electrostatics. And you see here, The extreme one is on the boundary, and the function is monotonically increasing or decreasing. And this is a problem because then if this persists in generality, we cannot create these traps. This is a bad thing, which eventually led to a Nobel Prize because someone solved it. But he solved it, the way he solved it was, we don't use electrostatics. So today what I'm going to explain, why you cannot build a trap with electrostatics because of Mr. Laplace. And later people solved it, but that was already not so long ago. I mean, this was in the 1960s. It's a guy called Wolfgang Paul. He got the Nobel Prize in 1989, and from there was all kinds of advancements in quantum computing is actually based on his traps. So, okay, so sometimes physics will tell you what is not possible, what is impossible, which is very important, and you know this from other fields, and I'll explain this a little bit today. So, the general claim is like this: what we cannot do. So I would like, I cannot plot the potential in 3 dimensions, so I'll plot it in 2 dimensions. If someone tells you that he found a charge configuration far away that gives you this potential, hopefully you understand what this potential is. Mm-hmm. This is the plane is xy. What is this? This is an harmonic oscillator in 2 dimensions, more or less harmonic. It doesn't have to be harmonic. It can be harmonic here and something else there. This is not possible with Laplace. And this is a pity because if you had this object, that would be a trap. That would be a stable trap.
That's impossible because of the second level of the derivative?
Yeah. Yeah, and we will show more generally that, yeah. So you can easily see this because if Vx and y is x squared plus y squared, in 2 dimensions I'm working, the second derivative of this guy will give you 2, the second guy of this guy will give you 2, and this is not solving the Laplace case. So this is impossible. On the other hand, this is with z. On the other hand, Vx, y, z, in principle at least, x squared plus y squared minus 2z squared is possible. Because when I take the second derivative here, I get a 2, a second derivative here is a 2, and here minus 2 times 2, that will give you 4 minus 4 will give you 0. So this is not okay, and this is okay. This is all multiplied by some constant giving you the right units. Let us say y equals 0, z equals 0. This guy is a parabola. This guy is a parabola. But what is this guy? It's an inverted parabola. An inverted parabola is an unstable solution in the sense that if you are on the top of this parabola, you are going to go down. And hence you cannot find these traps. And hence you cannot build these... if you cannot build the traps, then you cannot do precision measurements. And again, this is a problem. You can start thinking how to solve this problem. Maybe you can come up with some ideas that will... It's not so complicated ideas, actually. I don't know why it took so long. But people were struggling with this, again, up till 1960. This is even known before. And then this led to many, many measurements, because once people were able to trap ions and solve this problem, they could do precision measurements and later control, for example, ions. So let us go back now 1 second and try to formalize it a bit more. Go back to 1 dimension. So we said here, so I'm going to discuss the law of the average. and here the dimension is 1. And again, we have just a linear line. So we take a point x between x1 and x2, some point. This is x1, this is x2, this is x. And we take x plus delta. This point is x plus delta, and this point is x minus delta. What is the law of the average, which is a trivial statement for one dimension, is that the potential at point x is equal to the potential at plus delta plus Vx minus delta divided by 2. This is what I call an average. It's not a random variable, but it's just an average. It's the potential here, potential there. You take them and you divide by 2. That is an average. And this is very easy to understand because of the linearity of this curve. Because if I put x plus delta, then, you know, it's trivial. The b, here you have a b plus b that we had before, and it will be divided by 2. And the ax plus delta, the x will remain, but the minus delta will remain. It's very silly, very easy to see this. And this is called the law of the average. So what we see from one dimension is one thing. We have some law of the average, which is very simple. We also see that the extremum is on the boundary. That is on x1 or x2. Extremum can be either minimum or maximum, extrema. Okay, so let us see how this generalizes to higher dimensions. And actually, the two laws, the average and the fact that the extrema are on the boundaries, are related to one, actually related to one to another. So I have a complicated problem which I cannot usually solve. Let's say here V1 with some potential V1, and then here some volume V2 and potential V2, etc. And I'm at a point here, and at that point there are no charges, so Laplace equation holds. And around this point, I'm going to build a sphere. The sphere has a radius r. This is a theoretical sphere. It's not a physical sphere. It's just I put it there to define the average. So the law of the average is the average of what? Of the potential at this point. This point is some point r, small r in space. And when I average the potential that is created by whatever is in the environment, what will I get? The potential in the middle. So I have a sphere. You take all the points on the sphere, you sum them up. I'll define the average. You sum them up, you make them actually do an integral and divide by the surface of the sphere. Whatever you put this, you can put it this sphere whatever you want, and you can take r to be whatever you want. The average on the sphere will be exactly the potential here in the middle. So we were going to formalize it, V of r. So V of r, what is r? R is this point relative to some coordinate system. V of r is 4 pi r squared. R is the size of the sphere. So what is this 4 pi r squared? This is the surface of the thing. This is like I divided before with 2. Now I'm dividing by the surface of the sphere. Integral on the surface V of r, V general V, not V of R, V. Where is it? It's the V on the surface, dA. So what I have here is I have some small patches dA. In each, this is the sphere. Each patch has some small patch, has some potential. I take V at this point, multiply by dA, V, I sum them. This is the meaning of this integral. Notice that it's not these are not vectors. Sometimes dA appears as a vector and sometimes not. In this case, it's not because you're multiplying it by a scalar. This is the statement. This statement is a nice statement. First of all, it's just elegant. And secondly, for example, if you solve the Laplace equation in a complicated or non-complicated case, you can always use it to check your solution. It's one way. Okay, you worked hard, you made 22 mistakes, you pray to God that 11 cancels the other 11, and now it's okay. Okay, you got some answer, you can use this to check it. If this integral is simple, at least it's useful, or if you have a numerical solution, it's very useful, because it's also very flexible. Because again, what is R? Small r, and what is big R? Doesn't matter. So you can do it all over the space. But the second thing is that VR has no local minimum or maximum. No matter how clever is the engineer in putting all these charges, there is no local minima at this point because of this thing. Because obviously this V on the surface, let's say we take this point and let's say this is the point where the potential is minima in the middle, then obviously the integral, because the values of the V are larger by definition, the potential is minima here, so on the sphere they are larger. We can make also the sphere small as we wish. If they are larger than that minima, well, the integral has to be bigger because this dA will cancel out with this guy. So VR at the point where you are a minima is always smaller than the average, because all the potential on the sphere are bigger, VDA, and if it's an inequality, it cannot be smaller, and that means that there is no potential which is minima. And the same with the maximum, because the V maximum has to be larger. Max. So our max is some point in space where the potential, we assume it is a maximum. And we make an assumption, and then it's bigger than this thing, and this is a contradiction. So there's no such thing as a maximum and a minima. No matter what, you can work as hard as you want, and this is you cannot find it, which is a pity, right? But again, people have solved it eventually, and it's not. You just need to think a little bit out of the box, and maybe forget about electrostatics. That is the general direction that we should go. This law is also valid in 2 dimensions. I'm going to prove it in 3 dimensions, and I'm going to prove it simply for a single charge. And after I prove it for a single charge, based on superposition, it's going to be valid for any charge configuration. Maybe you can find better proofs. But by the way, if I have the charge inside, of course, and a single charge inside the sphere that I make, then obviously the maximum is exactly here. But this is not the point, because the point is that we have no charges inside this sphere, right? Otherwise, Laplace equation is invalid. So if I have here a charge, then of course the maximum is in the middle. So we excluded those charges. That's by our definition of Laplace equation, essentially. Okay, so what we would like to do is the following. We have this sphere, this theoretical sphere, and we're going to put its center. We're going to put on the origin. So this is of radius r, and then we are here. We're going to put some charge. This is like all these junk. I'm putting one charge. This contribution, this charge that will eventually walk from here to there, and then you'll have another one, etc., etc. So this distance we're going to call z, and then this is going to be I'm going to call r. This is from the charge to the surface of the sphere. Again, theoretical sphere. It will be called r tilde, and of course the potential on this sphere is going to change because the distance from the charge is going to change. So r tilde, we are going to integrate it eventually over this different angles here, and we know the potential here. This is a very simple thing because this is a single charge, so we know it, and we can solve this problem quite kind of easily. If you want this drawing a little bit, this is the drawing. R is given, Z is also given, and R tilde will be changing as I move along the surface of this.
Because of the direction of r hat? Because I mean the size of r will stay the same, only the direction.
Small r or big R? The big R is fixed.
Yeah, it just moves in.
What I said, the small r is changing. Because if I'm here or down here, it's not the same.
Yeah, okay.
This is what I meant. The small r is changing, the r tilde. And this angle is a famous angle. I mean, theta from the usual spherical coordinates that I think you all know. So what does the law say, or what we want to prove? We want to prove 4 pi epsilon 0 q divided by z. This is this distance. This is the potential here in the middle of the sphere. We claim that this is equal to 4 pi r squared. This is the law of the average. This is this surface of the sphere. Integral of the potential that depends on this r dA. This is the average. So now we need to plug in what is this thing. What is this thing? Okay, so in here what we need is this r tilde, and what we use here is this famous cosine theorem from high school. So what we have here is we have here r tilde squared. It's like Pythagoras, more or less, plus r squared minus 2z r cosine theta. So, and eventually the advantage here, we are going to integrate in this dA over this cosine theta. This is where we are heading. We will express dA in terms of the radius and theta angle. And now we are using kind of convenient coordinates. So let us write this integral. I'm not gonna, so we are at the beginning of the course, so we can kind of treat simple integrals just to refresh your memory. So what do we need to solve? It's not difficult. The average. This is the surface of the sphere. 4 pi epsilon 0 This comes from the potential, the usual factor, integral over d phi. This is the azimuthal angle, from 0 to 2 pi. We have an interval d cosine theta minus 1 to 1. Many times it's written as sine theta d theta, but I like to write it like that. Sometimes I write it like this and something like the other part. And now I need to write okay, I'll explain this. R squared comes from this dA. And then we have the distance r, because the potential is simply, we have somewhere here the q, wherever it is.
Ellie, can we use the point degree to solve this? Because it is a known theorem that for any line going through a sphere, the product of the length from Q to its two intersection points is equal to the distance of Q from the center squared. So just by summing these, we get that this entire sum is equal to the sum over all the distances averaged divided by z squared, and thus we obtain the 1 over z factor.
The problem with your statement is that it was longer than the proof that I'm going to give here. So maybe you are right. I did not follow exactly what you said now. Let's talk about it later, but I'm going to prove it in one line. So possibly you are correct that it is known in mathematics in a different way, but the integral here is trivial. So let's do it and prove what you say. I mean, we are going to prove what you say. I think what you said is correct, but there was some resonance, and I didn't follow till the bitter end. So talk to me after the class and refine it. But let us just prove it. It's very simple. So I'm just saying that this is 2z r cosine theta to the power half. And this is simply this r, well, this is r prime, and this is just the usual 1 over r tilde potential. And now this is the reason why I wrote it as d cosine theta, because if you think about this as x and this is x, this integral is trivial because you just put the minus half, you're going to put on top, you look at the internal derivatives, etc., etc. It's going to be very easy. So let us write it down. This is equal to q over 4 pi epsilon 0. And from d phi I have 2 pi. From here I have 4 pi r squared. From this r squared I have r squared. Okay, so I use dA. This is what I'm using actually. dA is d cosine theta. d phi. This is dA.
R squared, no?
Yeah, r squared.
Okay.
So I have all this. Of course, this r squared will cancel, which is very good because the solution cannot depend on r. Whatever r you choose is good. And this is equal to the following: -2. This comes from the derivative of this half. It will have this -2. And then I have z squared plus r squared minus 2zr cosine theta divided by 2zr. This is at cosine theta 1 and cosine theta -1. And then this is equal minus q 4 pi epsilon 0 . Yeah, this 2zr comes from the internal derivative of this 2zr here. 2zr This one, yeah, you see 2, 2, 4, only 1 4 is left, and here I have the following. I have z squared plus r squared minus 2zr. Sorry, why didn't you correct me? Here I have a half. Here I have a half minus z squared plus r squared plus 2zr, the half. Yeah, but what is this guy? You see, this is z minus r squared.
This is r tilde.
No, I mean, r tilde depends on the angle theta. No, it simply is. Yeah, and with the half, it's simply z minus r. And that's the point. And this is z plus r. And this is good for us because this r and this r should cancel.
It's not always being an absolute value.
Yes. You mean, yeah, okay.
Depends if it's inside or outside.
But then you can cancel it. You can cancel it. No. Okay, so the z actually cancels here, and with this r will cancel with this r. So this r will be cancelled, and the z will go away. What is your question again?
It depends on if you're outside the sphere or inside the sphere, and then if you look at the permutation.
Yeah, but z is much bigger than r. You see here, z.
We're outside the sphere.
So we're outside.
This point is r. You are outside.
Yeah, so it's that minus.
Yeah, this is what I use.
A question?
So just let me summarize. This is what we expected from the law of the average, because this is 4 pi epsilon, and as I mentioned, z goes away, the r goes here, and here I have 2 of these r's, and then we get the expected result, 1 over.
Why are the R's all getting cancelled?
Z minus r minus z plus r. No, I said the r's are not cancelled, sorry, the z's are cancelled. And this r is cancelled with this r downstairs here. Then you are left with 1 z on bottom. Okay, it's clear, more or less. So we got what we expect, because this is exactly the potential at this point.
But it's not supposed to be an absolute value.
Again, because z, you see this is z, and z is bigger than r here. So z is always bigger than r in this problem. Okay?
So if we wanted to calculate inside the sphere, we would just flip r and z in this expression, right?
Yeah, but then the Laplace equation will be invalid, because then the q will be inside. And this is not part of the game. Then the law of the average does not work. Exactly from this reason. Okay, so we proved that there is no local minima, there is no local maximum, and we can average over some arbitrary sphere to get this potential inside. So just to summarize, in kind of schematically, in 2 dimensions only, you can have in 2 dimensions something like a saddle point. I don't know how to plot a saddle. Where you go down, and then you have a maximum. So you have a minimum when you go this way along the saddle, but you have some curvature on the other side. This is possible, but you can never have something like that. You can never have a local minima. So now, how will we trap ions? Any ideas? How did Wolfgang Paul get a Nobel Prize? There are two general ways of trapping in the world. This is beyond what we are studying now, but it's related to what we will study in the future, but we will not study traps so much. So I'm going to just give you general information now. One, there are two ways. So you here I have a stable point, and then here it's unstable. One way is to add a magnetic field. So let me ask you, first of all, let's say I have a constant magnetic field. You know this from high school. What will happen to an ion? It will move in circle. Is this a trap?
No.
Why not? It's moving. It's not, okay, let's say the radius is very small or good enough for us.
Oh, okay.
Is it a trap?
Yes.
No,
Why
because the z direction it's not trapped.
Ah,
So that is the problem. I mean, you need to block it from going up. So a small rotation if I have an ion, it's making small rotation, but then you give it a small tuck tip, it will start moving in the z direction forever. That's an unstable state in one direction, similar to what I'm plotting here with electrostatics, that in one state,
like the inverted parabola on the z-axis.
exactly like this saddle, very poor saddle that I'm pointing out. The same is with the magnetic field. So you cannot solve it like that. So there's one trap called the penning trap. And what this pennings are there for trapping is we're going to use both electric field and magnetic fields together. So here I have an unstable point in one direction because of the electric fields. We'll add stability due to one magnetic field. That is called the penning trap. But it's a trap that is based, because magnetic fields are based on velocity, because of Lorentz force, they are based on velocities. Wolfgang Paul had a very different idea, and his idea is we have to live with this instability, but we'll make it time dependent. So we take this saddle and we have this minima in this direction, and then we'll change the minima in that direction, and we'll oscillate it very quickly.
Okay.
This is his idea. I'm not going into the details, and you can read about it in ChatGPT. And this is called the Paul trap. So it's a time-dependent trap. It's not a static trap.
It traps like in y and then in z, and in x, y, and z.
Exactly, but it's not a trivial statement.
Yeah.
That's why I got a Nobel Prize, because is that stabling or not? But effectively, it creates a trap. And again, I'm not teaching this. Now, so this was done, let's say, in the 60s, the 1960s, the previous. And then after that, many people could use it in order to make precision measurements. And again, what is precision measurements? After you have the trap, that's only one stage. Then you can put different ions inside and you can measure them very precisely. And this led on not only Wolfgang Paul got a Nobel Prize, but other people got a Nobel Prize on the precision measurement based on his trap. So it was a big problem. It was only solved then. And then in the last, let's say, 20 years or so, or 10 years or so, this is a basis for certain types of quantum computers. So in quantum computers, there are two strategies. And I'm not talking about the quantum computing. I'm talking just how do you maintain the qubits, whatever they are. How do you organize them on the table? Because this is not a quantum course. The h bar is equal 1. There's no quantum in my course. H bar is equal 0. But in a classical computer, what you have bits, but they are organized on some matrix, right? On silica, whatever. And you put them on the table. You put one here, one there. And so two big companies called Google and IBM, they do the same for quantum computers, but they have qubits, which are some Josephson junction, doesn't matter. They don't have traps. There are other companies like IonQ and Continuum. These are companies that are worth $10 billion. I checked it. It's much less than Google and IBM, practically infinity. But okay, you cannot ask how much is the quantum part of Google worth. I tried to find out, but never mind. But okay, this is IonQ, and also Roy Ozeri and Weizmann is doing the same. They are trying to build traps. These are the Wolfram Paul traps. You have some traps, and you put inside some ions. There are different types of ions. So the commercial companies use very heavy ions, and the academicians try to make the ions not so heavy. So even what is the ions is different. It could be calcium 40 or whatever. So there's a huge split between these fixed in space qubit systems and these trapped ions. Now, what is the, so again, this is, let's say, IonQ. It's a very famous company in quantum computing. So what is the advantage of trapping them like this and not putting them on a matrix? The advantages and disadvantages. When you put them in free space, the environment is not acting on them because they are in vacuum. So the noise, according to IonQ, will be reduced. It's not accurate because there are other sources of noise and no one really says he has a quantum computer. But they are using these traps. And then their goal is we can manipulate each ion with these traps. I can have several traps. I can move one ion. It can be in one trap, another ion, and these are only 2 qubits. One ion in one trap, another ion in another trap. Then I can move the ion and we can entangle them or do all kinds of things together. So they are moving the bits. Like you imagine that you have a computer where the bits themselves are moving. They are trying to do that. Or if you want an analogy from your kitchen, there are 2 people who design your kitchen. You are the cook, and then you go to the fridge, you go to the stove, you go to the sink, and you move around among the things. And another option is the cook will stay in one place and the sink will come to him. This is the difference more or less between Google and IonQ, all these two philosophies. And you move them, and then you move them somewhere, and then they have to interact with some laser fields. So that's another type of electrostatics. Electromagnetism. Well, if you fix them in space, let's say in the usual traditional way, you need to bring the radiation to interact with each one individually. So you are moving the microwave that is interacting with these qubits in the Google thing, and you move it from here to there, instead of moving the atoms to interact with these things. Now, why am I telling you these 2 things? It's just saying that in the context of this course, there was a problem given by Laplace. It was solved by Penning traps and Paul traps. It was used in academy in physics for many years to just measure all kinds of fine structure of all kinds of atoms. And now part of it, at least, is moving into real applications. Maybe it will work, maybe it will not, but to design a trap, a good trap, is not a trivial thing. And it's all because of this Mr. Laplace. Okay, that was a general point of view on this field. Let us move on. Now I would like to prove the uniqueness of the solution. This is something that physicists don't usually do, and mathematicians always do. The reason the physicists don't do this is that if you have a good physical equation, like the Laplace equation, it describes a physical reality, and the physical reality has one reality, so there's only one solution, and there's no need to prove it. But it's actually not necessarily correct, because you might have 2 solutions, and maybe both of them solve the equation, and then by some noise you go to one of them and not to the other one. So I would not rule out the possibility that you solve an equation and then you have two sets of equation that satisfy both the equation and the boundary condition.
The Laplace equation is for when you have no charges inside your volume, right?
Yeah, sure. We mentioned
Okay.
this. But you have again the boundary. We're going to prove this uniqueness. Again, this is something, it's still simple. Just to remind you, maybe you saw similar things. So we are going to have some surface and I'm going to work inside. So on the surface, I have some potential. This surface defines the boundary condition for what you're going inside, and I give the potential itself and not its derivative. So there are different types of boundary conditions, and von Neumann, and we are going to use this this thing. So inside you have some solution, and let's see what it is. And so we claim inside, we walk inside, and we claim it is unique solution. So what does it mean unique? Let us assume that there are two. Assume we have two solutions. Call them V1 and V2. Again, what is the solution? It solves Laplace and the boundary condition. So now we can, we want to show that V1 is equal V2. That is what is meaning unique. They cannot be different. So we define V3 is V2 minus V1. Define this auxiliary potential. What is V3 on the boundary?
0.
Yes, exactly. Why? Because the first solution gives you the boundary condition, and the second solution also gives you the boundary condition. So this minus this gives you 0. So what is the equation for V3? It's the Laplace equation. So it's the Laplace equation where on the boundary, the solution is 0. Now we know there are no maximums and no minimas inside. So the solution, if it's 0 here, cannot be maximum or minima inside.
Must be 0 in the inside as well.
0 everywhere, so V3 equals 0 everywhere. And this is because there are no extrema. So if V3 is equal to 0, V1 is equal to V2, and there's only one unique solution.
Which means that if we find a single solution that solves the Laplace equation for...
You can go to the beach and smoke a cigarette. Yeah, if you find the solution, you are done.
Okay.
That's the practical way to put this. So, now let us remind you a little bit of how to solve these equations in Cartesian coordinates. Then we'll use spherical coordinates. And so in general, when we have some symmetry in the problem, we can use all kinds of methods, especially separation of variable technique, which is again something you know, but I'm very nice. I'm going to remind you about this a little bit. And we will see how these principles, the general principles that I just now discussed, how they are seen in particular solutions, and how this general insights can, you can more or less see the solution of the Laplace equation. So I'm going to solve an equation in 2 dimensions. The reason why I solve it in 2 dimensions is that when you have in 2 dimensions, the third dimension will be the potential function of xy. You can more or less visualize it when the potential is over x, y, and z, it's a bit more complicated to even see it. So let us go to a relatively simple equation and a geometry. V equals 0, there are no charges, and we have x and y, and I'll soon explain, and here it's also 0. So we have a slab, and the potential is 0 along this axis. This is at y equal a, and it's 0 at y. When y is equal to 0, it's also 0. This is this 0, and at infinity, these are these three dots. It's also 0. And the only place where it's not 0 is over here. It's v, let's call it v0 of y. So these are the boundary conditions.
Can you write them down?
Yeah. So on x equals 0, sorry, on y equals 0, and at y equal a, vxy equals 0. At x to infinity, vxy equals 0. This is this line. This is this. These are these lines. And v x equals 0. It's v. This is this v0 y. Later we will define what is this function, but we start with the general function. But already now we can kind of more or less see what will happen. Let's say this v0 of y is a constant. So try to plot it. So this is v0. How does the solution look without solving?
Like
It's like when you were a kid, you went to a slide and you went down, right?
Yeah.
Okay, so you start here and it has to go, but it also has to vanish like that, right? So, but something like that. Oops.
But if it's a constant, it will look the same along the
What do you mean it is a constant? Where is it a constant?
if v0 is constant, the function is
V0y, I took it as a constant. This is a constant. But why do you understood this? But why do I say it's going down? Why can't it have some oscillation or something? There's no extremum, and there is no. There cannot be a maximum and a minimum, which means that here in this case it just has to go down smoothly, and in this kind of arc like that, right? So this is the solution. We don't need to solve anything. But now, okay, what do we do in university? We take something very simple and we're gonna write an infinite series and solve it. But this is it. And the insight comes. You satisfy the boundary condition and there's no extremum, and then you go down. So what just now taught you, I think, is useful more or less to understand what are your possibilities. Okay, so let us see how this is translated into mathematics. So to solve the problem, we use a method that you are familiar with, which is called separation of variables. I define two functions and I multiply them. Now this solution is not satisfying the boundary condition at this stage. It's a general solution, some general solution. Later we will add all these solutions to create the boundary condition. So for a second, forget about the boundary conditions. Let us assume we have this type of thing. And the reason why we do it is then I can easily show, I can plug it into the Laplace equation. and then I will get, and divide by x times y, then I will get, I think you understand this. If not, tell me. This big X is a functions of small x plus y double tag y equals 0. Yeah, because I took the derivatives and then I divided by x times y, and then I got x, and the y was canceled out, and then I get this. Now this thing is nice because this function depends on what? Depends on coordinate small x. This function depends on coordinate small y. If two functions, whatever they are, one of them depends on x, one of them depends on y, for all x and all y, how can they be the same? It's only if these two guys are a constant. And this is what you do, and we can define this constant. And then we get, the advantage here is that we get two equations, capital X. I would like to write it with k squared, capital X. And the second equation is with a minus k squared over y. Here, I'm not saying at this stage if k is, in general, beyond our specific problem. It can be also complex valued. Actually, here I'm kind of choosing it in a clever way in order to make it positive. But if I didn't know that, okay, k can be a complex number, but I did here kind of use a small trick related to our problem. You'll soon see what I mean if you don't understand this. But then, simply said, these are trivial equations. Capital X is this function a exponent. What is a is a constant, some constant, I don't know it yet. Kx plus b exponent minus k x, and this is a function of x, and this capital Y is, I want to write it as c sine ky plus d cosine ky. Now you can say, why is this an exponential and this is a sine and cosine? It's the same thing. If k will become complex, it will be the same thing. You'll go from exponentials to sine, and from sine to sine hyperbolic, back and forward. Here I a little bit made it a bit simplified for this problem. I was a bit smart. So now we need to determine all these constants, or some of them at least. So if we choose k to be positive, then a is going to be equal 0. This is because, now I'm talking about our specific problem, because at infinity, if I have here x going to infinity, this will explode, and the boundary condition is at 0 at infinity. And this is because, so this is the boundary condition of our specific problem. And this is nice because then we have only one exponential function that is decaying in space. We don't know yet what is k. We need to determine k, but that will be soon done. So what we have is vxy. Again, this is a particular solution which satisfy one boundary condition at least, and later I'll sum up many of them to create the exact boundary condition. So this is ei kx. Okay, you can add here the b, but I don't want to. Sine, I'm just copying.
Can reduce the d as well.
Sure, that's what I'm going to do now. So the point is that if I know that Vx at y equals 0, remember this this is y equals 0, this is y equal a, is 0, so this function is gone. Because if I put y equals 0, the sine is 0, but the cosine is 1.
Yes.
So this function is gone, and then I'm left here with only the sine and this one. So which boundaries did we use? You should always think, what are the boundaries I use? Because if you don't use all the boundary conditions, something is wrong. We use the boundary at infinity, we use the boundary here, then we're going to use the boundary up here, and then eventually the boundary here. So the last one is the more complicated one, quote unquote, because there we have some function v0 of y. So now we are left with this guy, so vx and y. So again, this is because the boundary condition is equal, I want to write it with a c, yeah. Ce minus kx sine ky. Now this satisfies the boundary condition y equals 0, but what about
Y equals A.
ya? So then we have the so-called quantization rule, even though we are not in quantum mechanics, where sine ka has to be equal 0. And this gives you a condition on the k. The k is going to be equal n pi divided by a. N equal 1, 2, 3 in principle, etc. So now we know what is k. This k enters not only in the sine, it also enters in the decay. So they are coupled in some sense.
Because they have to be equal to satisfy the Laplace equation.
Yeah, because of both of them are equal k squared here and k squared here. So, and this is kind of expected because what is the length scale that we have here? The length scale is given by this length scale. So the decay in space is given by this length scale. So you see k is 1 over a, x over a. That's the scale of decay, but of course there is an n here, so it depends what n you choose. But anyway, this is the final. This is the solution. Now, as I mentioned, we didn't use one thing, and what we didn't use is we didn't use the final. What happens here, and that is, so I'm now going to change the notation. This is going to be a solution that depends on the quantum number n, and Vn xy. We're writing now as Cn exponential minus n pi x over a sine n pi y over a Now, can we, first of all, there is a boundary condition that Cn is going to be, this is a solution for some boundary condition, right? But when you see the sine function alone, what you can see is something that is oscillating in this y direction. Does it have a minimum and a maximum? Of course it does. So what is happening here? If I take this sine function, it is oscillating, right? This function is decaying. So this solution is something like that. You have solutions that are oscillating, but here is the instability. It is going down in this direction. Here you can have a minima, but it's a minima when you go in this direction, but then if you go in that direction, it's not. And then, of course, the law of the average is holding. So hopefully you can see it's going down with oscillations on top. But this point is higher than this point because of this decay. And that means that the law of the, you can check that the law of the average is working here. Yeah, but, you know, and that there's no local minima, a true local minima that, you know, both sides, it goes down. So this is this exponential decay that you can see here for any n. But now we want to have a general solution. And the general solution comes from the fact that the Laplace equation is a linear equation. Because it's a linear equation, we can add solutions with all kinds of Cn's, and these Cn's will be determined by this function that we said here, v0 of y, eventually. So we can write as a superposition vxy, sum over the n from 1 till infinity in principle, Cn exponential minus n pi x over a sine n pi y over a with infinite number of unknowns. So how do we solve this? How do we get the solution? So remember, this point is x equals 0. So v0 of y, which is the input function, this is the potential on this part of the system. Without it, you cannot solve anything. Is equal, what do I need to do? I just need to put in x equals 0 is equal to the sum n equal 1 infinity Cn sine n pi y over a. Now I go to my toolbox and I have to take one of my many tools out of my toolbox. What is the toolbox? What is the tool?
Fourier series.
It's a Fourier series, yes.
Orthogonality of the sine function.
Or orthogonality of this sine function. And the reason why I emphasize it is that later in more complicated problems, you always have this trick. You have it for the Gender polynomials, for Bessel functions, whatever you want. So you need to have a list of all these orthogonality relations, because without them you cannot solve many, many problems. So what we are doing now is a very simple example, but it repeats itself in many, many other examples. And then the orthogonality is the following, in this case, 0 to a sine n pi y over a sine n prime. So this n and this n prime are not the same, of course, over a dy is a over 2. That's the a. This integral is defined by dy. Y has units, so it has to be a over something n prime, where this is the delta of Kronecker. It's like a delta function. It's equal 1 if n is equal to n prime, otherwise it's 0. So this is what I call the orthogonality relation, also normal functions in general. And this is also, you can call it a filter. Why is it a filter? You see this equation? I can now multiply it from the left by sine n prime pi y a and integrate over y. And then what will happen, because here I have an infinite number of Cn's, I'll be left with 1. And this is good, because if I'm left with 1, I can know what it is, this 1. It will depend on n. So this is why I call it a filter of these Cn's. So we take this, we integrate from 0 to a sine n pi y, n prime type y over a, over this function here, dy. We use the orthogonality relations, and then we get the Cn. And we are done. Formally, at least we are done. So the Cn is 2 over a. This 2 comes, I think, from here. Integral from 0 to a v0y, whatever that is, sine n pi y over a dy. So this equation together with this equation, these are the solutions because I express Cn and then I need to sum the series. Of course, if you give me some function, I need to do this integral. It can be difficult, it can be easy, whatever. And then you need to sum an infinite series in principle. Usually we don't sum infinite series, but they are cut off. We need to see exactly where in space they are cut off, but usually you can sum up to a finite number depending on the values of the parameters. It can be more or less. The reason is, if I have here a very big n, then it's decaying e to the minus, and x is not small. Okay, so who cares? I mean, and if x is order a, e to the minus n pi, and n is 100, that is 0. So you can, at least x bigger than a, you can easily cut off this infinite sum and sum a finite series. Sometimes you're lucky and you can find Cn and you can sum the infinite series and get an even simpler expression. And this is the case for a constant potential. So let's say V0 of y is simply V0 independent of y. So we have a step here, and we are looking at 0 and 0, and we are looking at what happens in this case. So the Cn is simply, I just plug it in, it's 2 over a V0 integral from 0 to a sum n pi y over a dy, and this integral is 0 if you think about it a little bit when n is even, because you have a sine function. If you are, from symmetry, it will be equal 0 depending how many nodes you have inside. So this is a trivial integral. The integral of a sine is a cosine. And then you put in the boundary conditions, and then this is Cn is equal 0 if n is even, and it is equal 4v0 over pi n and odd. So in this case, the solution is Vxy is the sum over the n equal odd. This odd even is, if you think about it a little bit, it's kind of trivial because there's a symmetry, because the initial condition was symmetric, plus minus is the same. There's a middle point where they are the same. And then this is 1 over n. Okay, there's the 4 v0 over pi, 1 over n e to the minus n pi x over a. This was our k sine n pi y over a. This is the solution. Now, if you're a little bit a geek, you can put it into Mathematica or I guess chat and ask him to sum this series. Or if you have plenty of time, you can try and sum the infinite series by yourself. Now, okay, first of all, you can look at the solution. Let's say at x equals 0, and you can ask yourself, oh, how does it look when I cut off the sum? So if I cut off the sum when n is equal 1, so okay, again, I'm going back to x equals 0, where I know the solution is simply v0. But if I take only n equal 1 and eliminate all the others, I have, instead of an infinite sum, I just take 1, the solution looks like a sign like this. If I have n equal 10, it will look something like that. it messes up on the boundaries. And the reason is that if y is equal 0, sine is 0. And then it will give you 0. It will not give you a constant, right? So here, this is y equals 0 or y equal a. When you have n equal 10, you're not working well. And if you go to n equal 100, same problem will happen, but it will be in the middle, it will be smoother, there will be some fluctuations, and then it will drop here. But this width here, where it's not working well, becomes smaller and smaller as you increase n. So when you cut the sum off, there are some small problems that you need to think, and you easily find out why they happen. And when y is very small, you really need a huge number of terms to get the correct answer on the origin. So let's say this is n equal 100. Let's call this n max. But after 10, you more or less see the correct answer, even at the beginning. And for logics, it's even better because of the decay here in space. Now you can sum this series. But it gives you, I don't know if this is even worth it. If you want, you can sum the series. You can get a simple expression. Simple, it's not so simple actually. So Vx and y, sum in infinite series, is given by this strange expression. Inverse tan, arctan, sine pi y over a, sine hyperbole pi x over a. So it's a crazy expression, I admit, but sometimes you can sum this series up. Instead of using an infinite series, you get this series. I don't know if this is worthwhile or not, but it's kind of cute. Okay, so let us now go for 10 minutes break, and then we will discuss spherical coordinates and some, and especially the problem with this cone, which is a bit interesting. So yeah, let's have 10 minutes break. A break with no alarm. Hopefully. Oh, no alarm up to now.
Ellie,
Yeah.
is it okay if I ask you a question?
You can ask. It depends how long the answer will take.
I just want to ask why can we assume that K is not complex?
This is, in general, what I said in the class is that in some problems, the way I define the solution, K will be complex. But what we did here, I kind of put in an assumption, then I check the boundary conditions. The boundary conditions are satisfied with the K, which is not complex. And then because of the uniqueness of the Laplace equation, you get that this assumption that we had was correct. But to put it differently, in an exam, for example, in your homework, you don't need to assume that it is real. For example, I gave you two solutions in the x and the y coordinates. Remember, one of them was exponential, and one of them was with cosine and sine functions. This was already, I did a little bit, I already guessed the solution there. I could put both of them as exponentials, or both of them as sines, and cosines and get a complex value k, but then everything will be more ugly. So the way my point was, you can always do things brute force where you get complex k and all kinds of things. But if you have a feeling to the problem, you know how to define the problem and the solution. Again, I use here the fact that the potential along the y direction was 0 and 0, so I already guessed this sign solutions, you know. I had some knowledge here, how you can say it. And then the solution became very elegant, or not very elegant, but much easier than if I would assume in generality some k, and then prove later based on the boundary condition that, you know, one cosine function is actually a cos hyperbole function. It will be a mess. Is this a good answer? So I gave you two answers. One is mathematical. We guess it, and then we see that this is a solution based on the boundary condition, and then uniqueness defines it. This is a mathematical answer. In a physicist answer, we understand the geometry of our specific problem, so we know where it's going to decay exponentially. Then we put exponentials decaying, and where we're expecting a kind of symmetry, cosine and sine, and then we don't need to worry about this later. Is that clear what I said?
Yes, yes. Thank you very much.
So yeah, there is an art here, and that's why your homework is so important. When you do the homework, you know, you have a feeling for the solution from the beginning, you can massage a little bit the solution, and then the algebra becomes much more doable. Otherwise, you usually make mistakes, or at least I make mistakes. So these are the small tricks that you need to practice.
Okay, thank you.
You're welcome. So I hope most of you are back. So now we are going to solve the Laplace equation in spherical coordinates, and we will treat the second part of this lesson. We will treat this problem, which is an elegant problem. But generally we'll have some system with some spherical symmetry. As I mentioned before, maybe two spheres or something like that. And in these problems, there are different domains as usual, either inside this cone, outside this cone, down here. And in each one of these domains, we solve the Laplace equation. That is, there's no charges outside here. It's not with ice cream, this cone. It's empty. There's nothing in here. And then we have down here also. So there are three regions in space actually in these type of problems. Actually, two of them are going to be trivial. So when we have the Laplace equation, then first of all, like before, we need to write down the Laplace equation. Now we explore the symmetry, which is spherical symmetry. So the Laplace equation looks, I'll write it down like this. D over dr, r squared, dv dr, plus 1 over r squared sine theta, d d theta, sine theta, dv d theta, plus 1 over r squared.
Excuse me, Eli. There's another alert in Kiryat Anu, so
Okay.
might be on soon.
Take care of yourself. I'll just end the Laplacian and then we'll go. Yeah, please go to the safe room. Okay, so we are solving spherical problems now. And I wrote down the Laplace equation. I'm using here the spherical coordinates r, theta, and phi. I think you know them. You know what is theta, you know what is phi, and you know what is r. You want me to write it down to show the coordinate? No. You don't want me to write it. And this is the Laplacian, which I'm sure you saw. We want to solve it. And the general method is similar to what we did in the previous class. We're going to do separation of variables. We have orthogonality. We have different boundary conditions, etc., etc. And yeah, so the first part I will follow simply what is in Griffiths. And then I'll show you there is a problem with some set of problems where Griffiths is not giving you the whole story, and possibly something that you don't know. So we will soon introduce famous, so what are the famous functions that are associated with this, you know? What are they?
Spherical Bessel functions.
Spherical harmonics. What do you mean?
Spherical harmonics.
Yeah, spherical harmonics, which are based on what the polynomial? And the goal of the second part, so you don't run away, would be to show you that the Legendre is actually only a subset of solutions, which is not actually always true. There are some subtleties when the z-axis is hidden, so to say, that you need something which is not Legendre. That's the whole point of this class. So the first part will be, I'll remind you of Legendre solution of this type of problems, and then I will show when it doesn't work. Okay, so what we do, okay, so first of all, we don't like theta and phi, so we employ additional symmetry. So we assume that there is also, for example, in this problem, hopefully you understand what I mean, or this problem. So we have some potential V1 and V0 and V1 or V0, but it can be many things. But the point here is that the azimuthal angle phi, you have under the rotation of this angle, the system looks the same. And then we can simplify, we love it, because then this part is going to go away. If you don't have this, then it becomes more ugly. Then you have the spherical harmonics. But I'm a professor, so I'll do the easiest part, and you can do the one with additional breaking of symmetry. So essentially, in this I'm going to just ignore this, and then, okay, that's good. We are left only with two parts. So now, what we do for the first step is to write the potential. I don't remember the functions. Yeah, the functions now under this azimuthal symmetry depend only on two coordinates, r and theta. And if they depend on two coordinates, what we will do, we will define a function which is a function of r, and another function which I'll write like a big theta of theta. And this is a separation of variables. We can put it in here. Why can we separate variables? Because when this is gone, you see this guy and this guy are actually also gone when you multiply by 0. And this part depends only on r, and this part depends only on theta. So, yeah. So this is what we are going to do right now. We plug it in. We then divide by these two guys, and then we have a function of r only and a function of theta only, like we had before, but then it was x and y. And then we have two equations, which are simple equations, relatively speaking, one of them for the capital R and one of them for the theta. And these equations are given by some constant, and I just write it down. I'm not going to do it because, first of all, we spent a lot of time on many things, and I think this is kind of known. Or if not, you can do it yourself quite easily. So this guy is going to be equal LL plus 1. LL plus 1, this is like the K that we had before, and L is going to be an integer. The integer comes from the fact that actually from the theta, the cosine theta, when you add a pi, it will be the same thing. But this L is an integer, equals 0, etc. In quantum mechanics, this is going to be the angular momentum. So this is one equation for R. which is easy to solve, and so soon we'll solve it. And the same constant has to go into the zeta dependence. And this, okay, this one will be another d over d theta, which is essentially this one, sine theta d capital theta d theta. Then you need the constant, which here it comes with an L with a minus sign, because you remember both of them are on the same side of the equation. That I say both of them are L plus 1, L plus 1, but then I kind of...
Aren't you missing 1 over sine theta?
Yeah, but I didn't finish yet. Here I'm writing it as sine theta times theta. And these are the two basic equations. So this is the sine theta that you were talking about. And these are the two equations. Again, maybe I skipped a few details, but it's very easy to get them. Now, what we do is, as before, we solve it, this equation, the R equation. And let us solve it. And it's very simple to solve it. The solution of R is some constant A, R to the power L, plus B, R to the L plus 1. So what are we having here is, like before, actually, before we had an exponential growth or exponential decay. Here it's not exponential, it's R to the power L. So it's a kind of a power law, and the reason is here very easily. Let's say this solution, I take the derivative, then I'll get the first derivative, we will give you this L when I put this one in, and then I'll be with L minus 1, then plus 2, that will give you plus 1, then the second derivative will give you L plus 1. You can see, at least for this guy, that this is a solution. And again, what you typically have, let's say we have some sphere, so we have inside and we have outside. When we have inside and outside, then inside we would like usually to avoid the divergence of one of the solutions, then we'll throw one of them away. And also, if the potential is 0 at infinity, when we are outside, we would like to avoid this divergence. And again, it's similar. You can already start thinking about this problem, because what is inside and outside, what is small r and big R, is already not so clear in this geometry. We'll come back to that later. Okay, so we have the radial dependence. And now we have this zeta dependence. And what is the solution of this guy? You said it already.
The polynomial, Legendre polynomial.
Polynomial Legendre, but there is a small lawyer's comma of cosine theta. And this is this theta. This is, in Griffiths, he doesn't explain anything about this, but he says, if I remember correctly, provided that the z-axis is not missing outside of the domain. And you see here it's missing. When we solve here, then there is issues that we will soon discuss. Actually, those are the interesting cases. So this function is given here. And already you see something a little bit strange, because there's only one function, Legendre. Why aren't there two? Here we have two, or exponential, and but there's only one. And this is sometimes this is wrong. And okay, so this is this polynomial Legendre, and then okay, let us make a little table. The 0 of x. What is x? X is cosine theta. Yeah, and then what is this function? This is 1. And this is trivial, because if I plug in 1, this, okay, sorry, if L is equal 0, this side is 0, and then if you have here 1, then, okay, it is satisfied. P1 of x, you remember what it is?
X.
It's x, and this means it's cosine. And P2 of x is, if I remember correctly, 1 minus x squared over 2 or 3, I don't remember. Oh, here I have, sorry, like this. 3x minus 2, 1 over 2. And okay, the trick is you can change this sign into a derivative with respect to x, and you can get this, and then this x again is the cosine. And then there is the so-called Rodriguez formula, which gives you all the Legendre polynomials, or you can have tables, and of course you are allowed to use these tables in your exam. For example, let's take this one. Let's do it quickly. So you see, here I'll have a sine theta, derivative of cosine theta, that will give you another sine. Yeah, then I'll have sine squared, take the derivative. I'll get a cosine times a sine. And here I have a sine times a cosine. And L plus 1, L is equal 1, it give you 2. And one of the derivative of the cosine will give you, so you can more or less see it for this case and this case. And for this case, you need to work and plug it in if you have nothing to do in your life, and show that this is the solution. So the bottom line is that now the solution is given by an infinite sum. The infinite sum now is not over n that we had before in the Cartesian coordinates, but over L. So V, R, and theta, again, no phi because we assume some symmetry, is equal to the sum over L. And L goes from 0 to infinity in this case. In general, AL, RL plus BL, RL plus 1. This is simply these equations where I added an index L, because these are special solutions not related to the specific boundary conditions. PL cosine theta. And essentially, well, we're nearly done because we need to define what are these ALs and what are these BLs. So the way we do it, let's do one example, but it will be very general in my opinion. We look at a sphere, and okay, given a sphere radius of the sphere is going to be r. This is a real sphere. There's a potential on this sphere, and the potential is V of theta, V of r of theta, which means on this sphere, I assume that different points theta have different values, something would can be very general. And this is the boundary condition, and I'm working inside. Inside there's no charge. If there's no charge, I can use the Laplace equation, and then this is the solution. So what do I immediately get? Because I'm working inside, it's very important that I'm working inside, and the opposite is done outside. If I'm working inside, I want to kill this divergence, BL is equal 0. Wow, you can say, why do you kill the divergence? Maybe it exists, but if there was be a divergence, that this will explode at r equals 0, that's a maximum, but we know that there's no maximum, right? So it has to go away. So BL is equal 0 because we are working inside. And then we are left only with these ALs. How do we find these ALs? Like before, with a orthogonality relation. Now you need to go to your toolbox again, take out it, well, you find out the toolbox, whenever you want, and this is this orthogonality relation, PL cosine theta, PL prime, so we have two different indexes, L and L prime, cosine theta, sine theta, d theta. Okay, this is equal I don't bother too much. I'm not proving anything. I'm just taking it out of the book. So you know what it is when L and L prime are different. It's going to be 0, like a delta of Kronecker, and then you have some normalization. And the normalization is 2 over 2L plus 1. So happens to be. Please don't ask me why, because I don't care. I mean, this is the answer. You know, you can plug in 1, you'll get easily this answer here for L equals 0 at least. Okay, so this is the answer. Now, again, we take BL equals 0, we multiply on R equal big R. So now we work on the boundary and we multiply by this function, this filter, what I called before. Take these guys to 0, use also the orthogonality. This is based only to the integration of a theta. It has nothing to do with the small r. This will give you a filter. Only one of them will stay on this side. That will leave you with the corresponding AL. And that will be related to the function, again, when R is capital R. So with this orthogonality relation, we find AL is 2L plus 1 divided by 2R to the power L. This will come from here. See, this is capital R because I'm putting here capital R. This will be capital R. Then it will go downstairs when I divide. So here is the capital R inside. Integral from 0 to pi, same as this one. Then you have PL cosine theta. The potential on the sphere, whatever that is, the boundary condition, sine theta d theta, and this sine theta d theta is the same as this one. So this is the AL. So this is a formal solution because I now determined BL, I determined AL, and I have this infinite sum. Formally, I'm done. But maybe we would like to gain some insights, so let us use an example. So phi r theta, I'm going to take as a special function, some constant, which has units of volt, sine squared over theta over 2. It's not clear why I choose this example, but soon you'll see that this is actually an elegant, a little bit elegant example. But it's not, at least for me, not when you write it like this, you actually need to eventually move into Cartesian coordinates. But let us see what happens here. So what is the trick? The trick is we want to express this function. So you could just take this function and plug it in here. And then you could try and solve this. And then, wow, okay, you can ask ChatGPT if it will solve it to you. But how do you solve this type of integrals?
You can try to express your function as a polynomial.
Thank you. Want to replace me? So exactly that. We are going to use again the orthogonality relation. We are going to take this function and express it as a sum of polynomial legenders. But then you say, wait, well, we have here theta over 2. But polynomial legenders, you have the first and the second one is 1 cosine theta. So what you want to do is instead of having here theta over 2, you want a theta, because that's what's in Legendre polynomials. Maybe a cosine would be great. What? No. But first of all, we don't use spherical harmonics because we don't have the phi. And the spherical harmonics are related to the Legendre. So from my point of view, you can think about the phi angle as m equals 0. It's not part of this game. So the point is that this function can be written easily as P0 cosine theta. What is P0? That's simply 1 minus P1 cosine theta.
Divided by 2.
Yeah. This, yeah, okay, yeah, right. And this function is, as you know, is cosine squared theta over 2 minus sine squared theta over 2. And then with the 1, you get 2 times sine. And yeah, and this is divided by 2. So this is essentially what we need to do. This, in turn, what we are going to do now is we're going to use this equation, and then you see what will happen eventually. What does this mean? It means that AL is going to be not equal 0 for L equal 0 and L equal 1. So you'll have only two contributions, though this infinite sum, instead of summing over infinite number of terms, we're going to sum over only of 2, L equals 0 and L equals 1. And this gives you VR and theta C over 2, 1 minus R over R cosine theta. So from this is 0. This one gives you R, the small r, here. This comes from the L equal 1, and it's multiplied by a cosine. This is this cosine, this is the P1. And the 1 is with L equals 0, so this is R to the 0, so there's no R dependence, and then it's just a constant. And this is P0. This is the solution. Now, this solution might be intuitive or not intuitive. This is up to you guys to decide. But first of all, we can check. What can we check easily? What we can check easily is, so what does it mean, first of all? We have this potential, and this potential has this strange shape, sine theta, so it's, here it's 0, here it's 0, here it's, no, here it's, yeah, here it's theta over 2, that is 45 degrees actually, which means this is a half, so here it's C over 2. So it's not a trivial potential. And we are looking inside. And what happens here in the middle? Well, you just take R equals 0, so here it's C over 2. Why am I mentioning the middle? Because this is something I can check. You can also check always your solutions. Why can I check it? How can I check that this is correct? This is what I talked in the first part of the course. Yeah, the average theorem. So what I need to do is I need to average over the boundary, which is the given. This is the boundary condition, and this average should give you C over 2 if I did not make a mistake. So this is one example of how you calculate, use the average theory. The V average is 4 pi r squared. This is the size. So what am I doing here? We have a real physical boundary, but I'm putting on it another boundary, which is a theoretical boundary, and I'm averaging over that boundary. So what we need to check is that sine squared theta over 2, this is this value which is given, it's part of the solution, times C dA. What is dA? This is this d cosine theta, 2 pi r squared. So I'm integrating over the shell of the sphere. I'm not going to do this integral because of all the alarms. but we know the answer and you can check it. This gives you C/2, and I'm very happy that I didn't make any mistake. It's very simple to do this integral. I'm not going to do it because of it's already a bit late. Yeah, it's very late. But still, I'll continue a little bit. I hope no one will kill me, except for the Iranians. This problem is a bit maybe not intuitive, because what are these cosines, sine squared? But if you look at the electric field, this is another check that you can do. First of all, you always want to, sometimes you want to look at the potential, and the potential looks reasonable. I think in the previous problem, you didn't need the electric field because it was going down and it was smooth, but here, okay, maybe you have good intuition, but I don't. So sometimes it's better to look at the electric field. And the electric field, you can do this problem by yourself, turns out to be super duper easy. Well, not exactly super duper easy, but it's when you work with spherical coordinates. This R comes from the solution, minus C over 2R sine theta d theta. And then if you think about this a little bit, this solution just in Cartesian coordinates is C over 2R Z. So what we have here from point of view of the field is simply a constant field inside. So just to give you some intuition, here I have R, here I have dr is like that, and here I have d theta is like that. And because I have here sine and cosine, when you look at it and calculate where is it actually directing to, it is directed in the z direction with the minus signs. I'm just telling you this, but it comes from here, from simple algebra of and the fact that these two factors are the same. So this is simply dz, if you want. So this is the E, it's very simple. Now you should do one last check of sanity, which is here very simple. This is, by the way, what I found in exams very perplexing, because people get all kinds of answers and they're totally non-physical. I don't mind if you do a mistake, but if you find a non-physical answer at the end, you might as well say this is not physical, and then I know that at least the physics you understand. Why the simplest check of this guy, what is it? How will you do? I mean, at least I would check this in the following way. This is the E. What should it satisfy? I go back previous lesson. It should satisfy the Gauss law, of course. We can do it by integration if you are willing, but there's no need. Also integration if I add here some flux in and the flux out are the same, but you can take the div E. Div E is equal inside 0. Why? Because there's no charge. Why there's no charge? We are dealing here with the Laplace. There's zero charge inside. So, of course, if you have a constant, then it's trivial that this Gauss law, the differential Gauss law, is holding. So we have div E equals 0, which is the charge inside, which is okay. At least this is working, and we are happy. So now I know that I should stop, but laws are given to be broken. You need to go.
The meeting is still being recorded.
I think so, yeah.
It is.
Yeah, I know. I apologize. If you have other better things to do or some other course, simply go and then come back and see it on the recording. Okay, so what I want to solve now, or quickly solve.
The YouTube live is stopped.
What does that mean?
גם ביוטיוב וגם במיטר, זה ממשיך לעשות.
But okay, they tell me, guys, that the Google Meet is still working, so
And it's been recorded.
and it's still recorded. So I think they're saying everything's okay. let us try. Which means they can view it, but not in live, right? Yeah, it's a bit a pity, but what?
No, they can view it live, just like he asked you the question.
No, but he said it's not on YouTube. I don't understand who.
No, it's
Each
both on
class
YouTube and
is
on,
being,
and on Google Meet.
Yeah.
But you can only access it right now on Google Meet. But it will
No,
be
okay,
later
I
on
didn't know
YouTube.
that some people are watching it live on YouTube. Okay, I thought it was only Google Meet. Okay, so now we want to do
I
something.
don't think that the Google Meet is being recorded as well.
It is, the answer it is. So now we are going to solve at last some problem that is not in Griffiths. And this is this problem. So we have a cone. Here we have V equals 0. Here we have V0. And there's an opening angle for this cone, alpha. And this opening angle, this cone, its tip is touching the surface. This is actually a caricature of a scanning tunneling microscope. So you can think about this tip as something that is actually exploring the topography of this thing. And there was a Nobel Prize on this. It's related to quantum, but the structure is exactly what we have here. Clever experimentalists can make a very sharp tip. Of course, it's not exactly a cone, but that's a different story. And also the surfaces are usually not exactly flat, but we are simplifying. And we have this problem. And what we want to do is we want to calculate the electric field. There is a potential V0, and we have here 0, so there will be some electric field here. And close to the tip, it can be very strong, maybe, when the tip is touching. And if it's strong, then you can use it. The scanning tunneling microscope, you get a current because of this thing, but it depends on the distance of the tip from the surface. So we are taking the easiest case where the tip is on the surface. In reality, you will have a little distance between them, only for the reason that you don't want the tip to break. But also, when you make this, then there'll be some current flowing, which depends on the distance. And then you go along a surface, and then if you have a bump in the surface, you can say how high and how low it is. So you're checking the topography of the surface. But again, like in the previous problems I mentioned today, it's a combination of electrostatics and quantum. So I'm just teaching you a very small part of the problem. And we want to solve this type of equation. And then we have 3 regimes, actually, down here, here, and inside. What is the solution of Laplace down here? V log the, so it's 0.
Yeah.
Because
we have a 0 condition, a boundary condition.
Right.
And
so all the boundary conditions that are on top, you don't care about them for what's going down here, and everything is very simple. You have the boundary, this surface is going plus minus infinity. Here I have Laplacian equals 0, the boundary condition is 0. At infinity, okay, what is the meaning of the 0? At infinity is also 0. There's no maximum minimum, so down here the potential is 0. Similarly, inside the potential is also a constant V0. But we really care about what's outside. In the third regime, this is the important one. So what we do is we go to Griffiths and we take the book. We take this equation out of our toolkit and we scratch our head. Let's look at it. So we have sum L equals 0 to infinity, AL, which we need to determine by the boundary condition. AL, this was with R to the power L plus BL, RL plus 1, PL cosine theta. Then here is the problem, this is R. You can look at small r, you can look at big R. And you don't know what will happen because what we said before that we have inside and outside doesn't hold here. So for small r, if you don't want the divergence, because why you don't want the divergence, let's say you're going out here, you expect the potential to be either V0 or V, but not infinity. So you cannot diverge, like we said before. On the other hand, at infinity, you have to go to 0, so you cannot have this one. So this means, what does it mean? It could mean L equals 0. Only L equals 0. But this is non-physical. If L is equal to 0 and BL is equal to, only L equals 0 and BL is equal to 0, then you have, this one is not diverging, it's okay, it's a constant. But then PL 0 is 1. This is not physical because that means that the VR or theta in this regime is a constant, but we know it's not a constant because we have two different boundary conditions, unless V0 itself is 0, but that's stupid. So this is not physical.
But if L is 0, then there is the solution of lambda.
Yeah, but this is my point. So, but my point is that the polynomial Legendre by itself does not solve this problem. And the reason is it's related to this log, is that in this axis is not part of the boundary here. This is the hidden z-axis problem. And the whole point is exactly, okay, so you landed, I don't know where, with Jonathan or?
Yeah, with Jonathan.
Okay, so Jonathan already taught this. I'm sorry, I didn't know that. But there is another, so there is another type of, he taught exactly this problem?
No, he didn't teach this problem. He just mentioned that that the polynomial Legendre when excluding the tips.
So we will go one step forward and we will look what are these other solutions that we threw away. So similar to here, we have two types of equations. Actually, here we have another equation. And we have to go back. Where do we have to go back?
To the definition of the
To the equation. So we had before, we had d over d theta, sine theta, d over d theta, big theta, which is a function of theta, minus L plus 1 sine theta, capital theta. But from, again, what I said before on the radial part, what is L? Now I'm choosing the L. L is equal to 0. Otherwise, you'll have problems here and here. So this is good because this is going to be simply 0, which is a good thing. Wait, one second. So to solve this equation, let us do a little bit of the math. So what we do, we first of all define x like we had in polynomial Legendre. It was a function of x, which was cosine, right? We do exactly the same. X is cosine theta. And then dx is sine theta d theta with the minus sign. And then this equation, okay, let us write it here. I'm going to write it, I'm going to divide by sine theta, this sine theta. So here I have sine theta, d theta. Why do I do that? Because this is essentially dx. So I divide this, but I can divide it by sine theta because here I have 0. So it is okay. Here I'm going to divide by sine theta. Then I'll have here sine squared theta, right? So here I'll have sine theta squared sine theta. This is simply this sine theta, d theta, theta equals 0. What is sine squared theta? By this definition, it's simply 1 minus x squared. So here we have d over dx. You have a minus, but you have another minus here. 1 minus, again, this guy and this guy are going to be dx. So here we have d dx theta. This is the solution. This is the equation, sorry. And this equation, well, one equation, this is L equals 0. One solution is simple. Make here a constant, and then it's a solution. But there is another solution, which is what Jonathan once mentioned, and this is called functions Q. Why Q? Because P and Q come together, polynomial Legendre, and these are other types of polynomials, but here we are only using one of them, 0. L is equal 0 because of, again, because of these R's. I only need one of them, thank goodness. And then this is equal 1/2 ln 1 plus x, 1 minus x, plus some constant d. This Q0, what I mean by this is this theta function. When you plug in x cosine theta.
Isn't it just outcome?
No? Why do you say that? It's not, this is ln.
Yeah, but this identity of
Hyperbolic counting.
Hyperbolic alternate.
oh,
Yeah, but for me, ln is more simple than. Ln is more basic. So, okay, we can check this. I mean, what is the derivative d over dx over ln 1 plus x divided by 1 minus x? This is 1 over 1 plus x. I take the log of the up. Then I take minus minus plus 1 minus x. This is 1 minus x squared over 2. And then you see this one and this one will cancel out. You'll have here d over dx of 2. So from here we get that this equation is satisfied. This equation. Again, this gives you 2 over 1 minus x squared. This will cancel. You will get a constant here, and another derivative will give you 0. So this is the solution. Now, essentially, we are done because all what we need to do is plug this solution here with L equals 0, not an infinite sum, and we get the solution. So, well, we still didn't use the boundary conditions, but that will be the final step. So the general solution is going to be this solution. Okay, so V, and it's interesting because only L equals 0 is here, it's the potential itself does not depend on R, the small r. It depends only on theta, and the reason is that there is no scale here. You see, this thing stretches to infinity, and this thing stretches to infinity. There is an angle, alpha, which is the opening, but you cannot say, I identify some length scale. In the previous problem, when we have this slab, we had the length scale, which was A. And then R, or X, or Y, or whatever, went with A. X over A, Y over A, etc. Similarly, from the sphere, we had the radius. But here, there's no scale. And that's why we are eventually getting a function of theta only. Maybe this blows your mind, because when you think of the electric field, but it is okay. Soon we'll see what is the electric field. The electric field does depend on R when you take the derivative. So it's not that you lose the R dependence, which would be a bit strange, because then, you know, the potential here and here is independent of R, but the electric field does depend on R. Soon we'll go back to this. But at this stage, we have this solution, some constant, ln 1 plus cosine theta, 1 minus cosine theta, plus d. The cosine is simply because x is cosine theta, And this is what we get, but we have two constants. And what are these two constants? They depend on the two boundary conditions, on this angle alpha and on this angle, which is this flat surface. What is this angle? Pi over 2. So we can immediately plug in pi over 2, cosine pi over 2. That will give you, what is cosine pi over 2? 0.
0.
Yeah, of course, because sine is 1. So this is ln of 1, that's 0. So what do we immediately conclude? V equals 0, because V of pi over 2 is equal 0. This is the boundary condition, again, on this flat surface. So D is equal to 0. That's good. We are only left with C. So C is determined by this angle alpha. Alpha is given here. So when you have alpha, you get this number. So to satisfy this, then the final solution is V of theta, V0, which is the potential on this cone. And then I simply have log of 1 plus cosine theta, 1 minus cosine theta, ln of 1 plus cosine alpha, 1 minus cosine alpha. So all this junk is this C. And you see that if I plug here alpha, theta equal alpha, this would be ln of something over ln of something. That will give you 1, that will give you the V0. So this is our solution. Then you can simplify it a bit, because this whole expression, this is tangents theta over 2. Maybe this is what related to what you said before. So this, you have ln of tangents theta over 2, ln of tangents alpha over 2, slightly more, slightly nicer. And then what is, just to finish this, what is the electric field? So the electric field, I need to operate with the del operator and get the electric field. But the del operator has units, of course, because, it's 1 over distance. And the only angle that is important, the only part that is important is the derivative with respect to theta in the del, because this function is a function of theta only. You don't need to care about the other derivatives. So E is simply given by 1 over R. That's the scale. So it's not an intrinsic scale of the geometry. These guys don't have a geometry, but simply where you are in space. That's why this appears here, d over d theta, v of theta in the direction theta. So if I'm in some point here, this is the direction of the electric field. And yeah, well, it depends if V0 is positive or negative, but I think you understand what I'm saying. And then if you plug it in here, what you get is that E is the following, minus V0 log tangents alpha over 2, 1 over R sine theta, theta. I'm not doing the derivatives. But what does this tell you? It tells you that, first of all, the direction. First of all, remember sine theta cannot be 0 here, because theta is always bigger than alpha, unless alpha goes to 0. So there's no divergence because of this sine theta. Theta is between 0 and 2 and pi over 2. Somewhere here. It's not, you cannot go down, of course. So this is the limitation here on theta. So it does diverge, but it diverges because of R. But where does it diverge? Here. this is on the boundary. So it's not a contradiction to what we said before, because remember we started the class one dimension, the maximum and the minimum were on the boundaries themselves. Here they are also on the boundary. When r is equal to 0, you are down here. So this is not a contradiction, and then it just goes down when r becomes bigger and bigger. But from a more physical point of view, you see that the electric field here is very strong. So close to the tip, strong field, which is expected, but this is exactly the idea of the scanning tunneling microscope. You can create a relatively high field. Of course, again, as I mentioned before, you don't put it on the surface, you put it a little bit up, and then you have this tunneling effect, which is a quantum effect, which has some current, and then you can measure the distance between the tip and the thing. So if you want to read about this more, this is called STM, scanning tunneling microscope, where again, we didn't do any quantum, of course, but this was the basis of, now we are going back in time, 1986, this guy Binning, he got a Nobel Prize. He comes from IBM, but not the quantum IBM that I mentioned before. Then it was not quantum. Nobel Prize, he comes from IBM Zurich. Okay, so here we will finish. In the holidays, you have time to read chapter 3. We will come back, we will deal a little bit more with chapter 3, especially about dipoles, etc. And then, we'll move into fields in matter, which is chapter 4, etc., magnetic fields, and then hopefully we'll manage to promote this course quickly enough. See you then after the holidays, and enjoy your holidays.
I have a question.